What's good, everyone? In this video, we'll be continuing on with the Triton Inference server series. I started this way back in terms of being able to serve PyTorch models using Triton. Just wanted to carry on. There's still a few more backends and kind of workflows that I want to talk about that might be handy if you're working with either traditional ML models or even large language models. So just kind of wanted to overview that and also present you this as a serving option there. Specifically today, we'll be talking about the Python backend and how you can kind of bring your own custom dependencies or packages if they're not natively supported by one of the Triton server backends. And before that, right, we'll revisit very briefly what a model server is, and then why specifically Triton is a great model server that you can use, and when to specifically use the Python backend that Triton exposes behind the scenes. And then the bulk of the video we'll spend on our hands-on, and if you want to just directly hop to it, the code's down below in the description. You can take it and play around with it as you want as well while watching this and going along with it. But really quickly, right, what I want to revisit, as I was saying right there in that little kind of mini table of contents, is what a model server is. And when we think about ML, right, or a ML model, whether it's a trained model or we're grabbing a pre-trained model from anywhere else, the real value of machine learning is only of a model is only recognized when you're able to expose it in an end application, right? So if you train your model, that's great, but how do we actually integrate it into our software application? And how do we scale it to be able to handle hundreds or maybe thousands of kind of concurrent requests as they're coming in, right? And for that, we need both a model server and hardware. And as you can assume, the hardware we're going to be using AWS, or you can choose a cloud provider of your choice here, basically. This is actually the compute juice, or kind of really like the compute that we really need to be able to scale up to handle kind of traffic coming in. But it's not going to work if we don't have an intelligent model server fronting it and also utilizing the resources that we have accessible to us from that compute. So the responsibilities of a model server is one, expose your serialized model artifacts as an API. So like I said, there's not much value in just having your model data or model artifacts dumped in some sort of notebook. You need to be able to expose this kind of as a REST API that you can interface and work with. So that's one thing the model server does, and there's different protocols. Obviously, you could go with gRPC, traditional kind of HTTP endpoints, whatever it is, right? Depending on what the model serving engine supports, you can expose it as needed here. And via this, you can actually integrate it into real-world applications and actually like invoke it, right? Invoke the serialized model. The second thing it does is it interacts with the hardware available. So no matter how much compute you have or how powerful of a node or instance you have behind for what you want to host your model with, if you don't have an intelligent model server that's able to understand the traffic that's coming in, the model data that you have, and then the resources that are available to it, and does not understand how to kind of orchestrate all of that or give the parameters for you to tune as an ML engineer to be able to optimize that, then you're not going to really be able to scale up to handle traffic regardless of how big of a machine you throw behind your model hosting, right? So another thing it does is it loads the model in memory efficiently. And this is, once again, it's seeing the resources that are available in the compute that you have backing it. So obviously you need the compute. You can think of that as the actual muscle, but the model server is kind of the brains in terms of how to use that to handle everything that's actually coming in. And then it also exposes different parameters that you can tune. Maybe you want to scale up workers on a per model basis. So allocate a certain amount of CPU workers or threads for each model that you might be serving. Maybe there's some sort of batching you want to do of the requests, right? So this is on the server side itself. It's called, there's different names for this, like rolling batch, things of that sort that different serving engines expose. But maybe you want to optimize this. Maybe you want to be able to batch requests, right? And then also, as we saw with LLMs and the whole kind of LMI series, maybe you expose LLM specific optimizations such as tensor parallel or things such as kind of KV cache memory allocation or things of that sort, right? The main essence here is that the model server provides the runtime environment for loading the model and serving inference, basically. And to do this, it sees what compute it has available behind it, and then it exposes, right, efficiently this basically serialized model as a REST API that you can invoke, and seeing the compute it has behind and the client-side traffic that's coming in. More robust model servers expose both the parameters and also by native default nature, we're able to scale up and kind of handle the traffic while using the resources that are behind your hosted model, basically. And within SageMaker, this is not a SageMaker specific video, but if you remember, there's something known as model latency or container latency. And that's what's taking place within this serving engine, basically, as these requests are coming in. So it's very, very important to have an intelligent model server because number one, we need to be able to just even expose it as a API that you can work with. But then also, as your traffic scales up, you need to be able to have these different knobs and parameters that will let you utilize your hardware in a more efficient way behind it, right? So a lot of ML engineers, a lot of their work is around picking the right kind of serving engine to be able to work with your model depending on the different parameters that are there. So a lot of my work, for example, I haven't talked of it much, but even as an ML architect at AWS, right, is understanding these different serving engines, their nuances, and what you can play with, and then load testing different kind of combinations. Because for different models, there might be different parameters that you have to configure in each of these kind of serving kind of properties or files that you're working with, right? And for LLMs, there's a whole other ballpark or different hyperparameters that you need to tune. So a big kind of thing that happens in ML engineering before production grade deployment is understanding the right serving engine to utilize once you have your compute decided as well, but then also understanding, right, what can I tune within this serving engine? So it's very, very key to pick the right server here along with whatever compute you're working with. And on that point, why Triton, right? And with Triton, the reason it's so popular is it exposes a variety of backends, butchering some spelling and pronunciation here. But right here, in terms of variety of backends, what I mean, if you remember, I said it prepares a runtime environment to execute these different models, right? Where these models can run, basically. And with Triton, what it does is it exposes different backends for PyTorch-based models, for Onyx-based models, and then for VLLM-based models. And here we'll specifically explore the Python backend, and then another video we'll be making a powerful feature known as ensembles, where you can kind of stitch together multiple of these backends. There's also a few others that we might not visit in the series, but I encourage you to check out the different backend support. But in essence, what Triton is doing is via these backends, it's exposing efficient ways of preparing runtime environments to be able to serve these models. So for example, the PyTorch backend, the libtorch backend that we explored, it executes Torch C++ kind of based libraries underneath the hood for inference. I believe it's the C++ APIs there, but I would double check that there. With Onyx, it's leveraging the runtime, the Onyx runtime kind of client there to be able to conduct inference. And same with these different engines. Take a look at each of the kind of documentations for these backends, but it's essentially kind of giving the best way to serve different models of different frameworks and flavors. So it's a very framework agnostic model server that also gives specific optimizations with each of these serving engines, basically. So for PyTorch, there's PyTorch specific optimizations depending on what we're working with. And then through Onyx, like I said, exposes the runtime there. You can basically explore each of these depending on the type of model you're bringing. And it's basically almost framework agnostic essentially here. And then the reason today that we'll be exploring the Python backend, right, is that there are cases, just like with any serving engine, where you might have some custom dependencies that aren't supported. So this might be some proprietary packages within your own environment, or just some sort of libraries that you want to install, maybe for example on top of like something like Torch or transformers or anything of that sort. And this is especially key, right, when traditional workflows where you might have some sort of pre-processing, then you maybe have model inference with PyTorch or something, then some sort of post-processing, and maybe these different processing steps, right, are using some sort of custom packages or tokenizers or whatever you're working with, depending on your use case, right? So in these types of cases, Triton's introduced something known as Python Backend, where you can basically kind of build your own Python code with your own dependencies. But here we can extend the base container that Triton exposes for its serving engine and install those dependencies on top of it. So once again, anytime these are the kind of use cases here, any custom dependencies or proprietary stuff that you have that you might need to install on top of the base container, that's what today's video will be centered around, where we can kind of take a look at if you do have a use case like that, how can we go about it and how can we work with it? So with that being said, let's get hands-on. If none of this makes sense, it hopefully will soon in the video itself or the walk along here. And if I come here, I'm in my Triton server examples repo. I'll make sure to share this in the description as always. And what we're going to take a look at is basically how can we take the base Triton container, and you can see the latest and greatest containers and their kind of feature matrix here in terms of what you can pull down. And you can see what's supported, what's not supported, specific versions for different backends such as VLM and things of that sort. But here, we're basically going to pull down that container. This is in the conda Python Backend subfolder there, and extend it and add a few dependencies. In this case, I'm just going to add transformers and torch. Obviously, there is support for that through the torch backend natively, but this is just a bit of a proof of concept in terms of how you can bring kind of third-party libraries to the Python backend. So now, and I've also linked this, I recommend you check this out if you want to see the implementation for this specific backend in terms of how it's working there. But now what I'm going to do is I'm going to come into this notebook instance. I'm in SageMaker right now, a classic notebook instance, a G54X large. I don't necessarily need that to serve this model, but I'm just using a GPU instance type here for some other work here. So you can use a CPU-based workload here too, depending on the size of model that you're working with, obviously. I come here and I install a few different things, right? I install the Triton client. This is the Python client. It basically lets me send requests to the server here. You can also use the Python requests library too if you want. But then I install a few different things, such as you don't need SageMaker here, but I install transformers and torch. The reason I'm doing this is I kind of like locally testing my model inference code before jumping into the model server itself. I just want to see it working in a notebook. Obviously, you could also just start up your container and adjust the code as you want there too. But it's up to you. I just kind of like locally seeing things play out. I come from that kind of Jupyter Lab kind of lifestyle when I was doing more data science work, basically, where I just want to see it out cell by cell. But fully up to you there. Now, the next thing, right, before we get into the actual code itself, is we're going to extend the base Docker container. So at this point, I think 2510 is the latest Triton server image here. And all I'm going to do is simply just take that as my kind of base container. I'm going to extend that, and all I'm going to do is install transformers and torch here. Let's say you want to integrate with something like SageMaker. There are managed Triton images there, but if there's not a version that's supported, you can obviously take this base one and expose the necessary kind of constructs to work with SageMaker Inference there as well. But here, all I've done is I've built this Docker file out, and then I build that image basically in this directory. So if we come here and I do a Docker images right here, you'll see that I've basically built this image, and that's all it's doing is taking the already provided and managed Triton server image there and installing transformers and torch. Once again, make sure you're executing this. It doesn't have to be in a SageMaker notebook instance. Classic notebook instance, just somewhere where you have Docker installed, because you're going to need that to be able to serve the model. Now, if we come here, I'm just going to see how this model inference looks locally. Once again, just to visualize with transformers and torch there, I'll see that there's some sort of basically text classification or sentiment analysis happening here. And we can see that right there. Next, like we kind of talked about in the torch video as well, Triton, just like any other serving engines, expects its model artifacts in a certain structure. Different serving engines such as torch serve, DGL serving, or TensorFlow serving. I don't know, I haven't used TensorFlow in so long. They all expose their model artifacts to be exposed in a certain way so that the serving engine can pick up on these artifacts efficiently or in the format that it's expecting. For Triton, it can be a little more verbose, but once you get used to it, the structure will start making sense. But essentially, we'll have a folder with our model artifacts. This is going to be the model name. So Triton expects a model name to be able to pick up and load. We'll call it sentiment. And then specifically for Triton, it expects a config.pb text file. And this name right here, right, in this configuration file, should match that folder subdirectory, just to keep things simple here, because that's basically going to say this is the model name that we want to pick up on. And then you can define your input and output shapes. For those of you that aren't familiar fully with what your input and output shapes might be, you can trace them, for example, for transformers, using transformers utilities there. But optionally also, many of these backends come with Triton autocomplete config, where it picks up on the shapes if you provide kind of a sample input and output. So you can also check which ones are supported there as well. But here, essentially, I define my input and output shapes and my dimensions I'm working with. Here, I'm going to expect a text, and that's going to be a string, basically, which I want to classify. And I'm going to return, basically, a array in terms of, I think it's the logits that we're generating here, basically, with the kind of score in terms of how positive it is, 1 to 5, and basically the score here as well. I haven't studied the model fully. I just picked a random text classification model there. And then here you can also see you can specify an instance group to be GPU. Once again, for each backend, there's also different serving properties that you can adjust. This is just a POC, so I didn't add more. But I recommend looking at the documentation for the different serving properties you can play with. This includes things such as worker count, which is CPU kind of worker allocation there, batch size that you might be working with if you're doing any sort of server-side batching that you're working with. Each serving engine exposes different things because once again, it has a different kind of optimized thing it's exposing depending on the framework that you're working with. So for example, with VLM specific serving properties will be exposed basically for you to be able to tune and play with. With that being said, right, for this artifact, we specify once again that model directory. We specify our configuration file, which is basically our serving properties. But then especially, right, the whole essence with using something like the Python backend is to have some customized code interacting with different libraries we might be working with. In this case, we're just going to use transformers. There's a few methods basically that are expected by the model serving engine. Like I said, every serving engine expects code in a certain format in terms of functions or handlers it's exposing, and then also your serving file and how all these different artifacts are brought together. Here, this initialize method is going to load up that model or any kind of code that you kind of want warmed upon the first request. And then we're going to execute the different requests. So depending on what's coming in here, we're going to parse for that input right there, right? So if you remember, this matches exactly with that config file. We're defining the input as text. So this name is what we're going to be parsing for using the Triton kind of Python util files right there. We parse that, we get that input text, we have any kind of inference logic that we were doing locally basically there in that notebook that we were working with, and then we can send back an output tensor basically. And once again, that sent underscore array maps with what our output name is here in the config file. So any kind of custom code that you have here, you want it to match over to what is in that config file as well, basically. Otherwise, it's going to error out because it's expecting and picking up on this as the input and that as the output, basically. So make sure to follow that structure there. That's within my model versioning directory right there. And then if I come back, I now have my model artifacts basically set up in the structure that's expected. Now the key part is, right, we just have to start up our container. We now have our exposed model artifacts, right? And you might have to adjust this Docker command that's here depending on the kind of location you're in. So this kind of directory right here, you want to adjust if you're not, especially in SageMaker, or if you're not working with this repo directly, you're going to want to adjust this. I think it might be a little different even in my Git repo here, but you want to adjust this basically to reflect wherever your model artifacts are. So wherever you're pointing to this kind of NLP directory itself that you're working with, that's what you want to be able to expose as your model artifacts. If you're on EC2, this might be slightly different here in terms of what you're dealing with, right? And then what I'm going to do is I'm just going to take this, since I have Docker installed here, I'm going to start up the container, and you can see kind of all the serving logs as this model server is starting up and loading your model basically. And if we walk through here, we'll see the configuration file that it's picked up on, if there's any kind of code that we're also dealing with. And as we come down here, we should eventually be able to see that our model is ready. So sentiment is our model name, once again, that we defined, and then that's the model version that we're working with there. So now that we have that ready, we can use the Triton client Python library to kind of work with it. And remember, like I said, you can also see with different serving engines, there's different protocols that are exposed. So if you want to use gRPC, right, especially for maybe something like a vision-based use case, you can also go that route. So now if I come here, I'm going to start my Triton client, and I'm just going to use the HTTP client here, and then I can send Inference basically, and you can see the requests being hit here within our terminal as well. And then we can also just loop through this to kind of reflect, and we'll see it goes through and runs Inference basically every time. I'm not parsing it up, so you can parse this cleaner and make it as part of a more overarching explanation here. But here I just did a quick loop so you can see all the different requests that are basically happening. That at a high level is when you can use, or how you can use the Conda Python backend with Triton Inference Server. Like I said, the popular use cases that I've seen for it is when you have proprietary libraries that you might be working with, and especially when you might have any kind of custom code or pre/post processing that needs to happen. And this will lead naturally or segue into our next video, which is Triton ensembles. So we might have, for example, a torch-based unit, which is using the PyTorch backend, the PyTorch libtorch backend, but we might have a custom Python backend that does some sort of pre-processing where we need some code some custom code to be able to handle the input that's coming in. So what we'll explore, right, one of the other powerful features about Triton that I didn't want to talk of too much now, but we'll visit a little later, or in our next video here in the series is using that ensemble mode where you can stitch different backends, which might be exposing different models or just even different custom code interfacing with different kind of custom libraries that you might be working with, right? So that's essentially where we can use the Python backend where, yes, you can use it standalone. I would recommend, if the framework's already supported, just using one of the kind of backends that natively kind of serves it, because there's optimization specifically for each framework and preparing the runtime for it there. But you can use the Python backend, especially in my opinion, as part of a overarching workflow where you might have multiple models working in conjunction, or more complicated or sophisticated ML workflows, right? That's where I've really seen it. So this can be a bit of a building block in a larger kind of piece that you're building out here. But yeah, at a high level, that's mainly what I had for today. Thank you as always for watching. If you have any questions, please feel free to leave them down below in the comments. I'll do my best to get back to it. If you enjoyed the video, feel free to leave a like and subscribe. And like I said, we'll come back with a lot more in the space, both for hosting traditional ML models and also large language models. Thank you, everyone.